Welcome viewers to the fifth lecture for the online series of lectures for the course of Dynamical Systems. In this lecture, we'll start our discussion with the example of negative gradient flows. So let me write it here for you. We're going to start our discussion with negative gradient flows. Negative gradient flows. Let U be an open subset of R to the n containing the origin zero. Let also B is a map from the open set U to the set of real numbers, and we want it to be a C2 function, and it needs to satisfy that Bx is x being a point or a vector in this open subset of R to the n, and Vx is strictly positive for all x belonging to the open set excluding the origin, and we want V to be 0 when we are at the origin. Okay, so also put f to be equal to negative gradient of that scalar function V, so that f becomes conservative, and for all point P in the open set, we consider the following initial value problem. Consider the following IVP. So let me write down the IVP for you. dx over dt is equal to f of x is the system, and this is the initial value. X at 0 is going to be the point P. Let us number this equation by 1. Okay. Now, in the case above, we first show that 0 is an equilibrium point of this function f from U to R to the n. 0 is an equilibrium point of f and also we want f to have no other equilibrium points in some neighborhood of the origin. Okay, so and if f has no equilibrium points in some neighborhood of 0, other than 0. So let me draw a picture for you. So this is the origin 0, and say this is the interior is BR0, so that this radius is R. Okay, And 0, we are first going to show that 0 is an equilibrium point of this function f, and we also assume that there is no other equilibrium point of f in the interior of this ball or in this ball. Okay, and also we don't want the system contain we don't want the system to have any other equilibrium point also on the boundary of this ball, so that we want this to have no other equilibrium point except for 0, okay, other than 0. Then if this is the case, then the omega limit point of the orbit of P is going to be just the origin for all P in this open ball of radius r centered at 0, which are sufficiently close to 0. Okay, so I'm not going to write it in detail here. It will follow in the following results. Essentially, what we are saying here is that we'll find a radius delta which is less than r, within which for any point P this will hold. This is what we are going to show. Okay. So for all P in actually B delta 0, this is going to happen. Okay. That's why we are writing here that for all P in this ball which are sufficiently close, meaning that P belongs to B delta 0 where delta is less than R. So such a delta exists that we are going to show. Okay, so let's get started to the proof of the results. So first, the result states that the vector 0 is an equilibrium point of the system given in 1. Okay, and 1 was that this system, right? This is the IVP. dx over dt is equal to f of x, and x at 0 is equal to the point P. This was equation 1. Okay. Now, this is what we need to prove. Here goes the proof. Let us choose a unit vector w hat in this open set, the open set that we started with, which is a subset of R to the n, and observe that for any non-zero time b at t times that unit vector, it means that it's a vector of modulus t, and this vector is directed at the direction of this unit vector, and v evaluated at that vector minus v evaluated at 0 is strictly greater than 0. Why is it so? Because we already know from the hypothesis of the statement that that Vx is strictly positive, for all x in u set minus the origin, and v at the origin is just 0. Well, it's important to note here that these two zeros, it's an abuse of notation, because the 0 inside here, inside the parenthesis, is a 0 vector of r to the n, and this 0 on the right side is a real number 0. Okay, so we have to understand which 0 is used. Is it the 0 vector or the real number 0, based on the context. Okay, we number this as 2. Now, dividing this expression 2 by a positive t and taking the limit t approaches 0 from the right, yields the following. Lim, so we divide it by t, and as soon as we take the limit, this is no longer strictly greater than, it's greater than or equal to now. T0 plus, we can rewrite t omega hat as 0 plus t omega hat, so that we compare the expression with the definition of directional derivative, and we divide it by positive t, and this is going to be greater than or equal to 0 now. Okay, so this is what I have written down in the notes, that we have to pay attention to the abuse of notation here. The scalar 0 and the 0 vector with n0 values, which is an n tuple of course, are both denoted by 0. This is an abuse of notation. So now the left hand side is nothing but the directional derivative of v at 0 in the direction of w hat. Okay, and we find it to be greater than or equal to 0. Okay. So let me erase this part since I need some room. Okay, so this guy is the directional derivative of the scalar function v along the unit vector w hat in u, which is a subset of r to the n. So now this implies that a gradient of v at 0, this is going to be a vector, right? Dotted with this unit vector w dot is going to be greater than or equal to 0. This directional derivative being equal to this expression of the dot product of between these two vectors is follows from the definition of directional derivative. Okay, so this is going to be our equation number 3. Similarly, dividing the expression 2 by a negative t and letting t approaching 0, letting t approaches 0 from the left yields gradient of v at 0, which is a vector dotted with this unit vector w hat, is less than or equal to 0. This is equation number 4. So we repeat the procedure we repeat the whole thing that we did for positive t, also for negative t, and take this limit, and we approach. So we arrive here. Okay, combining 4 with 3, one obtains that the gradient of v at 0 dot w hat is equal to 0, because it's less than or equal to 0, at the same time it's greater than or equal to 0. The only way both are satisfied is that the expression is equal to 0, and that happens for all unit vector in U. Okay, and that's only possible because if you rotate the unit vector for all such unit vectors, you're going to have this to be satisfied, and the only way you can make it happen is that the gradient of v at 0 is identically the 0 vector. Here again, what's the abuse of notation? So you have to be careful. So this is 0 vector, this is also 0 vector here. Okay, whereas this 0 is just the real number 0, which means that from the definition of the conservative field F, vector field F, see that F is just the negative gradient of V, so F at 0 is going to be 0. From the definition of equilibrium point, we see that 0 is an equilibrium point of F. Okay, so it follows that 0 is an equilibrium point of F in 1 QED. Okay. So now we move to the second part of our result, which we are going to call part B. Let P is a point in this open set U, and suppose that P is not an equilibrium point of F, then the function V is strictly decreasing along the orbit of P, that is V at UP of T. Okay, you see that here UP of T. So as you vary T, you get different points of U, the open set, and the collection of all those points constitute the orbit, right? So that's why we are saying along the orbit of P. Okay, this guy, this number is going to decrease with increasing T. Where UP from JP to the open set U is the unique solution to the IVP in equation number 1. Okay, and this is the maximal interval of existence, the corresponding maximal interval of existence, defined on a maximal interval of existence JP. Okay, so here goes the proof of this second part. Let JP to the open set U. This is small u and this is big U. This is just a curve, the integral curve, or the solution of the underlying ODE, and this big U is the open set that we started with in R to the n. So let this be the solution to IVP1. So IVP1 was this, right? dx over dt is equal to f of x, and x at 0 is equal to b. This was IVP1. Defined on a maximal interval of existence G sub p, okay, where we want p not to be an equilibrium point of f, where p is not an equilibrium point of f. Okay, so then by uniqueness we have the following. Then by uniqueness we have the following. F at UP of t is non-zero for all t in the maximal interval of existence. This is equation number 5. Why? Because if it were 0, right, you see that this is the IVP that we are considering, okay, and we know that UP of t solves this system, right? So if you plug in UPT here for x, then this left hand side would be the same as the right hand side. So if f at UP of t were 0, we would have from the left hand side d of UP of t over dt to be equal to 0. From the system, from the underlying system. And any constant real number c C would be a solution of this equation. Would be a solution. Just write would be a solution. That is UP of T is equal to C would be a solution. For an arbitrary C, arbitrary real number C. Violating the uniqueness of the solution. See, violating the uniqueness. And therefore, we can never have f of UP of T to be equal to 0. Okay? It is always non-zero. Okay, I need some room. Observe that. Now observe that by the chain rule one obtains d dt of this scalar function v at UP of T, okay, is equal to the gradient of V evaluated at UP of T dot this vector UP prime T. Okay, it's just the application of ordinary chain rule. Okay, so but since we know that UP of T solves the underlying differential equation, meaning that UP prime T is going to be equal to f of UP of T, right? Because UP of T solves the OD. So that we have d dt V of UP of T is equal to gradient of V at UP of T dot f of UP of T. This is equation number 6. Okay. Consequently, using the assumption that f is conservative, one obtains from 6 that ddt V evaluated at UP of T is going to be, so just replace this guy with negative gradient of V, and then you have, you have negative the mod of this, the norm of this vector, right? Negative of the norm of this gradient V of UPT. Norm squared, sorry. So norm squared, the square of the norm of gradient V at UP of T, to be more precise. and it happens for all t in the maximal interval of existence. This is going to be our equation number 7. Now, since gradient of v at up of t is non-zero for all t in jp as given in 5. Okay, what was 5? Okay, as given in 5. Let me write 5 for you again, which from the non-uniqueness we saw that f of up of t is non-zero everywhere. And since f is negative gradient of v, we obtain that gradient of v at up of t is always non-zero for any time in the maximal interval of existence. So, since this is non-zero, we see that this is strictly negative, right? Because of the presence of this minus sign, we see that this guy is strictly negative, and from which we see that v is strictly decreasing for all t in the maximal interval of existence. Okay. But the collection of all the points up of t for t belonging to the maximum interval of existence is nothing but the orbit gamma p, gamma sub p of p in the open set. Hence the function v is strictly decreasing along the orbit of p, QED. Okay. Now the third part of the results, I'm going to state it first and then prove it. So let me state the third part. For every positive r with the closure of the ball of radius r centered at 0 being contained in the open set U such that the closure of the ball, the open ball, set minus the origin, contains no equilibrium points of F, if this is the scenario, then there exists a positive delta such that the ball of radius delta centered at 0 is contained inside the ball of radius r centered at 0 for Okay. Okay. And for such a delta can be found, okay, such that B delta of 0 is contained in BR of 0, and for every P in that ball, the solution UP at T will belong to the closure of the ball of radius R centered at 0 for all T in JP intersected with 0, infinity. Okay, so let me draw a picture for you that will help you understand it more clearly. So for a given R, we will first construct this ball BR0. This is going to be the ball B. This is 0. This is BR0. So this is the ball of radius R centered at 0. Okay. And this ball is contained in the open set U that we start with. Okay, there is an open set. Okay. Now if I take the closure of this ball, meaning that if I solidify this boundary, and so then there will be no equilibrium point of F inside this ball, inside and on this ball, on the closure of this ball to be more precise, except for the origin. Okay. If this is the case, then we will always find a positive delta such that if I draw a ball of radius delta centered at the origin, that ball will be contained in this ball of radius R centered at the origin. Okay? Which means that delta is less than R. Okay? So such a delta can be found, and so that for every point in B delta 0, the solution UPT, so if I take P in this B delta of 0, this is B delta 0, the corresponding solution UP of T will belong to the closure of this ball. Okay? Which means that the open ball, including the open ball with the boundary included. Okay? So UPT is going to belong here in this compact set. For all T here in JP intersected with 0, infinity. So this is the result. So we'll try to prove it now. Okay, let's prove it. Let R is a given positive number such that the closure of this ball of radius R centered at 0 is contained in this open set U, such that the closure of the ball of radius are centered at 0, set minus the origin contains no equilibrium points of f, which follows from the hypothesis of the statement. No equilibrium points of f Now we put epsilon to be equal to the infimum of all the numbers v of x as x runs along the circle of radius r centered at the origin. Okay. Let me try to erase this thing, the earlier figure. Okay. So that you see that this was the initial ball, the ball of radius r centered at the origin. Okay, so this is the circle, and as you move along the circle, you get different values of v of x. Okay, you take the infimum of those values, and that is going to be epsilon. Okay, this is our equation number 8. So now an important thing to note here is that this infimum is actually a minimum. That is, it is attained on some point of the sphere of radius r, meaning that this infimum is attained for some point here on the sphere as the sphere is compact and B is continuous. Right? So it follows from the extreme value theorem. So check out the extreme value theorem in the context of metric space, and you'll see that why this infimum is achieved in this case, because the underlying space over which the values are attained is a compact space, and the underlying function is a continuous function. Okay, good. Now the boundary of BR0 is the compact set delta BR of 0. Okay, so this is nothing but this sphere. Okay, sphere is the boundary of the open ball BR0. Okay, the detailed notations are included in the lecture note. So you may try to consult the lecture note for the detailed notations. Okay, now since a Bx is strictly positive for all x in the open set minus the origin, this is how V was defined. Also, V is continuous also the boundary of the ball is compact. Therefore, as we have already discussed, by the extreme value theorem, in the context of metric space, there exists a point on the sphere x, which we denote by x mean, such that epsilon is equal to, this infimum is achieved, v of x mean, and that has to be greater than 0 from the definition of v. Okay, so this concludes that epsilon is strictly positive. Okay. Okay, now apply continuity of f. Now apply continuity of v, the scalar function, and v of 0 is equal to 0. These are the two things that we are going to apply now. There exists a positive delta such that for all epsilon, it's just the definition, the consequence of the definition of continuity. So we are using the fact that v is a continuous function at the point 0. So for all epsilons, for all positive epsilon, one has mod of x minus 0 as mod of x minus 0 is less than delta. It will imply norm of, is the absolute value of Vx minus V of 0 is less than epsilon, because this is just a real number, right? Because V is a scalar function. V of x is just a number, so is V of 0. So this follows from the continuity of the function, the scalar function V at the point 0. Okay, so this is just a number. So it follows from the continuity of the function at the point 0, and of course V of 0 is 0. That's what we are using here as well. That is mod x is less than delta will imply that that Vx is less than epsilon, dropping the absolute value since V is strictly positive away from 0. Okay? So it doesn't matter if we use absolute value or not, because it's the same, because V is positive away from 0. Okay, this is our equation number 9. Now it follows from the result of part B, then, which of course states that V is strictly decreasing, along the orbit. This was the result of part B, along the orbit. Okay. So this is what we are going to use, and from which it follows that V of up of t is greater than 0. T is a later time, so the initial time was 0, and dilated time is sometime greater than 0, and that is going to be less than or equal to v of p. I am telling you in a while why I am including this equality here. For all t in Jp intersected with 0 comma infinity, this is our equation number 10, and this equality holds because I'm going to so here this t is not strictly greater than 0. T can be equal to 0 since the t is greater than or equal to 0. This 0 is here. This is inclusive. Okay, and for that reason you have an equality here. Equality holds when t is equal to 0, as up of 0 is equal to p. If we had t to be strictly greater than 0, we would have had a strict inequality here as well, but that's not the case. T is inclusive, 0 is inclusive here, and that is the reason we have a equality here as well. Good. So this is our equation number 10. So let me erase this part. Okay. So from here, this was equation number 10. We immediately see that if norm of p is less than delta, Now it follows from equation number 9 that if norm of p, just replace x with p, if norm of p is less than delta, then v at p is less than epsilon. It follows from 9, right? So that using 10, one arrives at the following. One arrives at the following, and which is what? V of up of t is strictly less than epsilon, since Vp is less than epsilon, so that V of up of t is strictly less than epsilon, and that is going to happen for all t in Jp intersected with 0 comma infinity. This is going to be equation number 11. So let me erase everything except for this equation number 11. Good. Okay. Now, here is the claim. We claim that 11 together with 8, what was 8? Let me write it for you here. Together with 8. 8 was the definition of epsilon, which was taken to be the infimum of all the values of v of x as x varies, as x moves along the x moves along the sphere of radius r centered at the origin. That was the definition. So this was 8. Okay. So now 11 together with 8 implies if norm of P is less than delta. Remember that where did we get this delta from? This delta was obtained from the continuity of this delta was obtained from the continuity of V, from the continuity of V at 0. So if norm of P is less than delta, then if this is the case, then UP of T is in the closure of this ball of radius r centered at 0. Meaning that you see that in the result in the part C there was a delta. We said that such a delta exists, and now here the claim is that this delta is precisely the one that we obtained using the continuity of V at 0. Okay, so this is the delta that we have found here. Now the claim is that this delta is going to serve our purpose, and this is going to happen for all T in the intersection of the maximal interval of existence with this positive real axis. This is equation number 12. So equation number 12 is a claim. Now we are going to prove it. So let me erase this bottom part. Proceed by contradiction. Proceed by contradiction. And assume that 12 does not hold. Okay. Then, if 12 does not hold, then there exists a time which is of course positive, T1, such that T1 also belongs to this maximal interval of existence, so that T1 belongs to this intersection. And the norm of UP at T1 is going to be greater than R, which means that we will be out of this closure. Okay. So it tells us that, so 12 tells us that for all time in this intersection, all the solutions will belong to this closure. Now we are saying, so we are proceeding by contradiction and assuming that there is a positive T1 in this intersection such that the solution at that time will be out of this closure, which means that UP at T1, the norm of UP at T1 will be greater than R. Okay. But we already know that norm of UP at 0 is equal to the norm of P norm of P is less than R. Why is it the case? Since norm of P is chosen to be less than delta, and delta is less than R by assumption. Remember that we assume that the ball of radius delta centered at 0 is contained in the ball of radius R centered at 0, meaning that delta is strictly less than R. Okay. Which means that norm of P is less than R. Therefore, we see that norm of UP of T for T equal to 0 is less than R. Okay, because norm of P is less than R. And we have also seen that according to our assumption, now we proceeded by contradiction, we have seen that norm of UP of T is greater than R for T equal to T1, right? This followed from the assumption that resulted in we assume by contradiction that there is a time t1 at which the norm of the solution will be greater than R, and at t equal to 0 the norm of the solution will be strictly less than R. Now we are in a state to apply intermediate value theorem that we are going to do now. Hence, by intermediate value theorem, IVT, there exists a time t bar in 0, t1. At t1, the norm of the solution is greater than R, and at 0, the norm of the solution is less than R. So there will be a time in between where the norm of the solution would be equal to R. Okay? Follows from the continuity of the norm and the continuity of the solution function UP. Okay? Thus, by 8, so 8 was the definition of epsilon, okay? Infimum of Vx, where x belongs to a point on the sphere of radius r centered at 0. So then by 8 one has V of UP T bar, since UP T bar is on the sphere now, and epsilon is the infimum of all these values, of all the values of V on the sphere, then V of UP of T bar is greater than or epsilon. Because epsilon is the infimum of all those values. So if I pick up a value on the circle, if I pick up a point on the circle, this is a point on the circle, at that point the value of V would be greater than or equal to epsilon. Okay. Here I have written down that since epsilon is the lowest possible number attained on norm of UPT equal to 0. Okay, good. But what is it? This thing is in direct contradiction with 11. What was 11? 11 was this: V of UP of t is strictly less than epsilon for all t in this intersection of JP with positive real line. This was 11. Okay, this was equation number 11, and this is in direct contradiction of this equation 11. So, which means that 12 must hold. 12 means QP of t is in the closure of this ball of radius r centered at 0 for all t in JP intersected with 0, infinity. This must hold. QED. Okay, so we are done proving part C. So I think I'll take a break here. I'll state part D and prove it in the next segment. Thank you for attending the first segment.